Alright, we are live.
Red light turns on whenever he hits it like that.
Well,
Yeah.
Did you read the instruction manual?
Shut up.
I mean, did you actually read it?
I've probably had this board longer than you've been potty trained. So.
I mean, have you actually read the
I
manual
beg
though?
to differ. I was pretty good at potty training myself.
That would look good on a college resume.
Yeah.
Potty trains himself.
Potty
Well,
trained since birth.
If I'm not potty trained, that's gross. It's dirty.
But you potty trained yourself though.
That's dirty.
I'm
not a fan of
Stop,
dirty.
this is biology. Stop.
I don't believe it.
Okay.
Biology's not real.
Biology's amazing. What are you talking about?
The door's over there.
Zip it. Okay, so part A, now this is, we haven't technically gone over the ideal gas law yet, but I know that is something you all did in Chem 2, right?
That's why this is everything in Chem Lab.
Oh, that's what we're doing.
That PV equals nRT. Now, if you're clever, and you are, first off, which graph are you even going to look at?
Probably the top one.
Just grab an entire stack.
One of each.
Sam's so confused.
One of each stack.
He handed me one.
Don't listen to any of them, Katie.
He's trying to trick you.
Okay. Now, here's what you have to be careful of. You have two different R values depending upon the situation. So you want to find the pressure, right? Okay? Now, at this point, you're flipping out going, wow, I don't know what the volume is. Well, look, what's on the left side? What are those units? Moles per liter. So if you're clever, what are you letting the volume be? 1 liter. Okay, that's kind of cool. So you've got nert over volume equals pressure. Now this is where you're going to run into trouble. You got 0.020 moles. I'm going to leave the R out for a second. Your temperature is what, 625 Kelvin. Okay. And then we're going to let that volume just be 1 liter because that's pretty easy to deal with. So you have two choices here. So here's the deal. Since this is in liters, okay, which R value do you want to use?
0.0.
Yeah, you want to use that 0.0821 per atmospheres per mole Kelvin. Because what do you want to end up in? Units of pressure, right? So your units of pressure generally are going to be one of two things. They're either going to be atmospheres or they're going to be kilopascals. So since you're in a chemistry class, they typically use atmospheres because they can. Because they weren't very good at physics, and so they did chemistry. So, which sounds horrible. So anyway, you should get a pressure around 1 atmosphere. Okay? Which is about what you all are under right now. Okay? You're under 1 atmosphere of pressure. Don't feel hard. Okay, yeah, it's good. Okay, now on the second part, they want to determine which one it is. So, what are you going to look at?
The two bottom graphs.
Two bottom graphs, figure out which one is
Linear.
and which one is linear.
The 1 over the constant.
1 over. So now, here's what's on your equation sheet. They don't tell you which one is first order and which one is second order. You have to know that. So since the inverse one is
Second.
so it is, there you
Second
go.
order.
So it's second order because 1 over concentration versus time is length. Boom, there you go. Now, on C, there's 2 ways that you can work C. Okay? Depending upon how you want to roll this. But one's a little bit tricky, okay? And I find it odd that they covered their butt on how they did this, and I'll explain in just a second. So, since it's second order, right? So there's 2 ways that you can do this. One option is that you can go just the rate law, and you can go, R is going to equal K times the concentration of, whatever it is, C4, whatever, C4H6 squared. Okay? Now, that's an option. So if you look at what you're given on that question, you're told the initial rate of the reaction, trial 1 is 0.001, calculate the rate constant K for the reaction. So if you're going to go with that, do you know the rate? Yeah, they gave it to you, right? Hey, you got the number. So the whole key to this, though, is that it's going to be the initial rate. So you have to plug in the initial concentration of that value. So the disadvantage of this is that it only works at the beginning because your rate's going to continuously change because of the fact that its concentration is going to be dropping. So what you've got to do is, if you're going to go with this route, and you can, and it's cool. Now, what is any rate measured in?
Molarity per second.
Molarity per second. Right? Now you have to have the correct units. So over here, I don't know, we'll leave the K out of this for just a second. But over here, that's going to be a concentration that's going to get squared. So that's going to get you units of molarity squared. So what units do I have to have for K?
1 over molarity seconds.
So I can go 1 over molarity second. That's cool. What else could I do?
The inverse.
Liters per mole.
Or I could just go molarity to the -1, S to the -1. Same thing, right? Okay? And sometimes you see it written as like the inverse of this, which sometimes you see it as liter moles seconds, which means the exact same thing, because it's the inverse of molarity, right? So either one of these is acceptable, just don't put a number. So if you do this, you get a K value of, I think, 2.5. 2.5. So, you know this. So basically, you're going to take that R, divide that by 0.020
Where's the R value?
squared. You know the R, you can get the K value. Life's good. Okay? Groovy. Got it. Fantastic. Now, here's your other option. And this is where the AP dug themselves a hole, because I've never really seen them do it like this. So this is one option. What's the other thing that you could do to find K? Use the integrated rate law. Okay? Now the integrated rate law is going to be 1 over A is going to equal KT plus 1 over A0. But here's, if you're going to go with this, okay? And I'm going to do this straight up like you guys are used to seeing it. And AP gave credit for this. Okay? So when you look at this, you know what the A0 concentration is. You go up there to the top of it, right? There you go. But you don't know these, so how could you find another data point? Yeah, just go to the graph. Okay? Go to that top graph and pick a time and a concentration. Okay? You can do that. So I went through, personally, I picked, I think 10 seconds and 0.01. So I came in here and said, okay, that's 0.010. And then I've got K, and then I've got my time, which is, I think, is 10 seconds, plus 1 over, there is a natural log there. And that initial concentration was 0.02, I think. Okay? Now, if you do it this way, here's your problem. Somebody do this. Okay? Solve for K, what are you going to do? All right, pretty simple. Take 1 over 0.01, subtract 1 over 0.02, and then divide by 10. What do you get?
5.
You get 5.
Wow.
Well, they actually gave you credit for this. If you did it this way,
Well, that's their fault for giving you a credit.
well,
Because it
because
makes
here's
them
why they
down.
were jerks about this. Okay? Here's where they were jerks. If you look at your coefficients, okay, and most of the time I've always seen this done where everything has a coefficient of 1. But if you look at the reaction, what's the coefficient in front of the reactant side? 2. So this should technically be 2K. At that, but look, if you make this 2K, and then you divide by 20 seconds, guess what? You get 2.5. Okay?
Wow.
So if you did it this way and you had 5, they actually gave you credit because most of the time everything has a coefficient of 1, and you kind of had to know that, wow, okay, this is a stoichiometric thing, and so that's going to be 2K relative because there's a coefficient of 2 in front of it. So I'm just telling you, but this is if you look on the grading rubric, it said, oh, we'll accept 5 because it was such a technical thing. But both of them should produce the same value of K no matter how you approach the problem. And that's why if you put that 2K, then you get the same answer as if you do it just using the rate law versus the integrated rate law. So that's the difference. Okay. Let's, while we're on a roll with Stoic, let's try the 2016 question number 6 with the barium and the etta. Sounds like Klingon. Okay, so stop yonder camera. So we're going to interrupt the previously scheduled broadcast for this emergency announcement. So when you're... Here's your PSA announcement. Okay. So you have K equals 7.7 times 10 to the 7. Is that a really, really big number or a really, really small number?
Really big.
It's really, really, really big, right? So here's the question. Do you think the forward reaction is really, really, really going to be favored? Or is the reverse reaction going to be really, really favored? The forward reaction is going to be really, really, really favored, right? So, if it's really going to be favored in the forward reaction, it's probably going to go until something is used up. So how can you figure out what's going to be used up?
Nice start.
Woo! Nice try.
You can either work in millimoles or you can work in moles. I don't care. Pick one. Okay, now let's go back to piece of peanut butter toast all day long.
Yum.
Oh my God, those are gross.
You're gross.
What?
Both toast and
Oh, that's
mini
right. I
wheats.
forgot you were the anti-toast.
Also the mini wheat thingies.
I like the frosted.
Those are
It's only
awesome.
this
Yeah, I
one.
hope you don't
This
spend
is
too much money on
only
that.
Hey, you know, I'm gonna eat a bowl of rectangular sawdust.
They're covered in sugar, though.
It's not enough sugar.
Yes, you.
Maybe if it
Are
were.
you talking about mini wheats?
Yes.
I know you're talking about just sugar covered sawdust.
I mean,
Dang
it's the
it.
same thing. It's like
I
stupid in
divided.
Texas.
It's
There's no
the
difference.
freaking.
Oh.
Oh my goodness.
Oh.
This is making me mad.
Let's not throw down the Texas
Or
card.
like
Texas
Texas,
is
am I
stupid.
right?
Yes, that's my joke from the other day.
I said it before you.
What?
No, I said the joke.
False.
I said the joke. That's
What
my
joke?
joke. More like Texas.
What's with everyone
Literally,
going against
2
Texas?
seconds after I said it, you
Texas
said it.
Everyone
No,
sucks.
it was my joke. Texas sucks.
I think it was
No,
Nicola's
Oklahoma
joke.
Actually-
sucks,
But
Nebraska
is
blows.
Kansas really any better? It's better than Texas. Texas is garbage.
Okay, anyway,
It's like even shaped like a garbage can.
yet again, Wheels has an opinion.
What a surprise.
Who saw that one?
That's you.
Okay.
Literally lately, everyone's like, "Oh, Texas is so dumb." I'm like, "Why?"
Born in Texas.
SpongeBob taught us.
You taught us the right thing.
Look, I want to get over this so I can go home. Okay? All right, so let me give you a little bit of background on some of the terminology in this question, because this used to be a big part of the test, these complex ions. So, complex ions are typically what you have is called a ligand. The ligand is the anion typically that bonds to your cation, typically, okay? Sometimes your ligand could actually be water, sometimes it could be ammonia. In this case, it's this EDTA. Now, so here's, and the nomenclature gets weird because you have to use these weird prefixes like tetraamine, hexaquo. And it used to be a key part of the test. So it's literally, it was this whole weird nomenclature on how you would name them. So complex ions, here's general background information. They tend to be colored in the sense like you guys don't do group analysis in Chem 2, but you would form these complex ions of like FeOH6, and they tend to be, because it's very, very bright, like brick red. And so complex ions, they're not on the test as much, but all they are is these big, massive ions. So here's the deal. Why does this have a charge of 2 minus?
Because 2 plus.
Yeah, basically it's simple addition. Okay, so you have a barium ion, which is 2 plus, and you would think that it would bond with this, and if you were to write a traditional ionic compound, you would actually, to make it balanced, you'd have to have how many bariums? 2. So you'd have Ba2 eta, okay? But because of the fact that it's a complex ion, this is why this still has a charge of 2 minus. Now, let's talk about the K value, which flipped Sam out, okay? So you have a huge K value. Right? And it doesn't say what it is, mainly because it doesn't apply to anything. But it's not an acid, it's not a base, it's not a solubility product. But you have a huge K value. So what's indicative of big K values? Forward reactions or reverse reactions? Forward. Okay, big K values. So that means this reaction is pretty much going to go to completion. That's the whole trick to that question. The reaction is going to go to completion. So, I did this, I worked in millimoles just because of the fact that it made the math easier. So, I got 10 millimoles of this, I think this is 15. So, the reaction, you can assume, just goes to completion. So, how much of your BA is left over?
None.
None of it. Okay, minus 10. Minus 10. That's so weird. So, I got 0. I got 5, I've got 10. But is that my concentration?
No.
No.
No, what am I going to divide it by?
100.
510.
How about by 100? So you should get 0.10 mole.
Got that.
Got that. Brilliant. Okay. Now, let's talk about B. You're going to take this and you're going to dilute this thing. So there's a couple of ways you can look at this. One is just kind of a common sense approach, okay? If you dilute this thing from 100 up to an entire liter, what do you think is going to happen to the concentration of this thing?
Go down.
Probably going to go down. So, but are you going to change, here's what's going to be important, are you going to change the entire thing that's in the system?
No.
No. Okay? Now, so you're going to still have the same number of things that are present. So this question actually was a little bit tricky. So you're actually, eventually, you will reestablish an equilibrium. Okay? You will reestablish an equilibrium. But here's what you want to look at. This is talking about right after that dilution. So we're going to dilute this stuff. So you're going to dilute it. This concentration of this is going to go down, so as this concentration goes down, the concentration of the barium ions has to go up. Okay? That was a legitimate option. You can do that. It's cool. Now, here's the other thing that you can do. You can look at the calculation of Q, which has mathematically the same thing as K, which is going to be products over reactants. So, okay, so that's going to be the concentration of my BA eta, okay, divided by the concentration of my barium ions and the concentration of my eta ions. Now, you're going to go from 1 to 1,000. So what's going to happen to the concentration of each of these, of all of them? They're all going to go what? They're all going to go down, right? By what factor? Because you went from 10 basically 100 milliliters up to 1,000 milliliters. So it went up by a factor of 10, so the concentration is probably going to go down by a factor of 10. So this concentration is going to drop by 1/10. So all the concentrations are going to drop by 1/10. Okay, so here's where this happens. We can just kind of cross those out. Okay, so I've got 10 in the denominator of the denominator, so the 10 flips up. So this is 10 times this, which means that that's 10 times Q. Okay? So Q is bigger than K. Nature flips out. Q is bigger than K. So mathematically, what has to happen here to get this back to equilibrium? If Q is bigger than K, what's going to happen? What's going to happen to these numbers up here? These have to decrease. These concentrations have to increase. Okay? You could give either answer. So if anything's going to change, look at a comparison to Q to K. And it works with QSP and KSP as well. If your QSP is a lot bigger than your KSP, what do you make? A precipitate, because you're going to shift the equilibrium back to the left. This Q is a lot bigger than the K. I'm going to shift that equilibrium back to the left. Okay? Good with that. Okay.
So what was the actual answer?
The concentration of your barium ions is going to go up.
It's looking for the amount of moles.
Yeah, it's asking moles, not molar. I just erased my answer for that.
Well, it's still got to go up.
Well, yeah, okay. If the concentration
super
goes up,
confused.
then the moles are, it's moles are going to go up.
Why?
I
thought, like, all you're doing is adding water.
like,
You do, but you're going to shift, but it specifically asks about the concentration of your barium ion.
it said the moles of barium ions.
Okay, but if you can shift this back, okay, but if your molarity is going to go up, then your moles of barium, the only way that can happen is if your moles of barium ions also increase. You can't have a higher concentration with, especially when you're increasing the volume, by having a smaller number of barium ions. So here's the deal. At the end of the day, your Q is a lot bigger than your K value. Nature flips out. These values get bigger. So the only way that these concentrations can get bigger, especially if you're increasing the volume, is if you have more moles of barium ions in those solutions. You're also, in the EDTA, they could have also asked about the EDTA. Both of these concentrations have to go up. The concentration of your BA eptica is going to go down. It was poorly worded because technically if you go back to equilibrium, then I kind of interpret the question as like if you go back to equilibrium, then if you let it sit long enough, you're going to go back to that same K value and the concentrations aren't going to change if you let it sit there long enough, kind of like with a QSP and KSP problem. So I think what they were, it wasn't the best worded question in the...
It says after equilibrium is reestablished.
But...
You have 100 and then
I know.
Which one is the solution?
I don't understand.
The solution they have, if you look at the scoring guide, they have two of them. But here's the dichotomy of this question, is that since it reaches equilibrium, when I first worked it, I said, well, you reach equilibrium, and it's going to be the same concentrations as it was before, because you're going to have the same K value. But how they graded it, they said, oh, we're going to look at right after you add the water. So,
But it says after equilibrium.
I know. Okay. When I answered it myself, I said the concentrations are going to go back to what they were because of the fact that you're going to reestablish equilibrium. But how they graded it was that they kind of punted the equilibrium part, which I found odd, and they said, oh, we're going to look at it right after you add the water. So
they get two more.
if it were me, I'd give credit for both answers. I'm telling you, how the College Board graded it is that they said, oh, this is going to be right after it to get to that equilibrium point. So that's why I didn't like the question. I didn't like the question.
So how do we know when they're just going to ignore one of the words?
Because right after you add the water, everything's going to become, these concentrations are all going to become smaller. Because you're adding all of that water.
But didn't we already decide, based from number A, that
Number A.
the only thing that's left that's there is but-edta? And there's no and there's no edta?
But the arrow goes both ways.
These 110s cancel out, you still got 110. Go back up.
Because the arrow goes both ways, you can reverse the reaction. So that's what they're saying. Yes, initially there aren't any barium ions. So when you dilute this thing by adding all of that water, it's going to shift this back and you're going to make more moles of barium ions. Because some of this is going to dissolve.
But I thought that was already dissolved. It says aqueous.
Oh my god.
I'm so confused.
Next question.
It's a complex ion. It isn't a precipitate. Okay? So, because these arrows go both ways, I can shift this back to where you make more BA and more EdTech. Now, if there was only one arrow pointing in one direction, they couldn't even ask the question because the reaction can only go in the forward direction. So because you've got those double arrows, you can reach a point of equilibrium. And that's what we're saying, okay, initially, this whole thing's going to go this way. Is there probably going to be a few barium ions left in there? Yeah, not very many. The vast majority is going to be over here. Just like if you have hydrochloric acid fully going to ionize, are you probably going to have some molecular HCl? Yeah, enough to worry about? No. But because this K value is so big, this will effectively go to zero. There's probably still some barium ions in there, just not as many. But when you dilute it, then this stuff initially is going to dissolve, which is going to increase those barium ion concentrations. Okay. All right.
Backside.
Of what?
Woo!
What's the backside?
It's page 16.
The 2015 number 3. The potassium, there should be one potassium sorbate. Tell me that's there.
Yeah.
Okay, let's do that one.
Sorbet. Sherbet.
Is it sherbet or sherbet?
Sherbet.
Both.
Neither.
Yes.
Sherbet is not a second R.
Well, it belongs there.
I thought it
Sam,
was sherbet.
let's just... Let's just not start down.
I spent plenty of time at the phonics station in preschool. There were dinosaurs there. I think I know what I'm talking about.
Shut down the camera. Okay, so 2015, number 3. First off, is potassium sorbate soluble or insoluble?
Soluble.
Why?
Potassium.
It's group 1 element, right? So, kind of visualize what's happening. We've got a stock solution of potassium sorbate. Student titrates 45 milliliters of the stock solution with hydrochloric acid using an indicator and a pH meter. Value of the Ka for sorbic acid. So since you have the Ka of sorbic acid, what is it? A weak acid or a strong acid?
Weak acid.
It's a weak acid. Now, 1.7 times 10 to the negative fifth. Is that a relatively strong weak acid or a relatively weak acid? It's actually a relatively strong weak acid, okay? Because the really, really weak acids might be 10 to the negative 15th, okay? Something like that. So it has a Ka value, but it's a relatively big Ka value. Now, so if you look at what's here in the beaker. So what do you have in this beaker? Stuff. You got some water. Okay. All right. Got that.
Some sorbate ion.
Some, or just put that just as your generic anions. And what else do you have?
acid.
I got some acid floating around, right?
Yeah.
Okay? Now, this is just in the beaker. Have we added the hydrochloric acid to it?
Not yet.
Not yet. Now, is this a buffered solution? No. Why? Yeah, well, I have added that. I haven't added the acid itself. Okay? So, to this, I'm going to add hydrochloric acid. Strong acid?
Yes.
Poster child for it, right? So, what's going to react with what once you start to add the hydrochloric acid?
Hydronium.
So, hydronium or H plus?
H.
Let's just go with H plus. It's a lot cleaner. So the H plus is going to react with your, whatever that formula is, C6H7O2, and what are you going to get?
Sorbic acid.
Yeah, you're going to make some more this. C6H7O2. Okay? So, there's your anionic equation.
You go to 7.
It's my favorite element.
Can you write an H after your C?
7, 7. What?
Not
Let's
that
not
one.
go on.
7, 7.
Okay.
He's gonna take your frustration out on the board.
Someday I'm just going to go, when I know I've got a brand new one of these, and it's
You're
my
gonna
last
punch
day
it.
teaching with this,
Kinda
it's going to
punchy.
be carnage. Okay?
You're gonna go Harlow on the board.
No. That death ray and that board. Yeah.
Oh!
Ooh.
Let's just do it without asking and then say, yeah, bro.
I mean, that's what Harlow did with his.
Why is there a hole in the board, Mr.
He
Bergkamp?
dropped it.
You can drop
No,
it.
but no.
Or you can actually
believe me.
throw the student.
Actually, the new one that I saw, that gets replaced, and then the whole board, this goes away, and my whole board becomes the smart board, where I can just write directly on the whiteboard, and then,
They should just make it like a giant phone, like a giant tablet.
yeah, that's basically it.
You don't
Okay,
have to worry about that.
all right.
We should just eliminate electronics from
So,
making these
now,
markers.
on B, a total of 29.95 milliliters of hydrochloric acid required to reach the equivalence point, right? So at the equivalence point, okay? At the equivalence point, what equals what?
This and that.
This and that.
Anion. No.
That's
What'd you say, Wheels?
That's
Okay,
equals-
at the equivalence point, what do you have a lot of to start with?
Those two.
These, right? Okay?
things.
You're adding a bunch of hydrochloric acid. So at the equivalence point, can you find out, since you're given, if you look at the information, you're told it takes 29.95 milliliters of 1.25 molar hydrochloric acid. So what can I figure out? The number of, or millimoles of hydronium ions. Okay, you got the stuff. So I can take 29.95 times, what is it, 1.25?
0.25.
So I can take 29.95 milliliters times 1.25. Okay? Now, at the equivalence point, that has to equal the same number of millimoles of this.
Yes.
But what do you have over here?
45 milliliters.
45
Milliliters.
milliliters. So what do you not know?
The molarity.
The volume. Now, is that volume going to be bigger or smaller? Excuse me, is this molarity going to be bigger or smaller than 1.25?
The smallest one.
Why?
Because you have a bigger volume.
Because I got a bigger volume on the other side. So what'd you get for that molarity?
0.8.
8, 3,
0.832.
2.
Nice. Nice.
Go.
Go team. Okay. So, base of the equivalence point, that'd be 2.54, which the following indicators would be the best choice. Mr. Flett, your thoughts?
On 3? Or C, I mean?
Yeah.
Well, if the pH of the equivalence point is at 2.54, really the only one that will actually change colors before that would be thymal blue and methyl violet. And I would choose thymal blue because it changes closer to the equivalence point.
Yeah, so go with that thymal blue, 2.0. Your pKa is closest to your pH. And again, this is going to play out large later on in the next part of this question. So you know your pH equals your pKa plus the log of your anions over your HA, right? So at the equivalence point, here's the whole kicker to this. At the equivalence point, what's going to happen to all of this? Okay. So if you look at what's going to happen here, right? So here's your pKa. Remember, that pKa is like the root of the tree. You can make this pH go up, you can make this pH go down. But it generally isn't going to change very much from this value right here. So just pick the one that's closest to that pKa value, which is going to be closest to that pH. Because that's going to be the root of the tree, and then you make that variance change from there. Okay. So go with methyl blue, or the thymal blue. Calculate the pH at half the equivalence point. Hopefully this should be the easiest question on here. What are you going to do? Half the equivalence point. At half the equivalence point, what do you know about these two concentrations at half the equivalence point? So this becomes the log of 1, which is 0. So your pH equals your
PKA.
Yes. So how are you going to find the pKa value? Take the negative log of 1.7 times 10 to the negative fifth, which should get you 4.77. Okay.
I did that right.
All right. Now, let's talk about the graph. Okay? Because there's some subtle things about this graph.
I didn't.
So they tell you, they've given you 2 points on the graph. Here's your volume of HCl that's added, and here's your pH. And here's 10, and there's 8. So even before you add hydrochloric acid, why is this pH up here? Why isn't it at 7? We haven't added any acid to it. We haven't added any sodium hydroxide to it.
And it starts with H's.
What'd you say, Wheels?
Because it's a weak acid.
So what?
It has the secondary reaction with the O's.
That really isn't, you're right, but let's be sketchy. Okay? So when you take that C6H7O2, right, and you dissolve that in water, it's going to ionize, right? Okay? So what's this C7H2 going to do with the water? Yeah, so I'm going to form some of that acid, C6H7O2, but what's going to be left over? Some hydroxide ions are going to be left over. So since we're going to have some hydroxide ions that are left over, guess what? That's going to shift that pH up above 7.
That's what I said.
Yes. Okay? But typically, though, when you talk about secondary reactions, it's like with the weak acids, or the weak base, strong acid when it's completely neutralized. But here, yeah, you're going to generate some hydroxide ions. Boom, here we go. So it really isn't a secondary reaction because that's the first reaction that's going to happen when you add that salt to it. Okay, so you got the curve, right? So the initial pH, okay, after the sketch titration on the graph, mark the position at the half equivalence point on the curve with an X. So here's 30, right? So where's going to be half the equivalence point?
15.
15, right? And you have that pH, which was what, 4 point? Okay, which is going to put you somewhere in here-ish. And this point over here is kind of down there towards that bottom. Okay? So, think?
No.
No. No.
Oh.
No. What's your other option? That?
A normal curve.
Still no.
A normal curve. Okay.
You're happy with
When you begin to add hydrochloric acid, what's going to happen to the pH? It's going to go down, right? So it really can't be this one. It's not going to be a linear function. So as long as you're somewhere close to hitting these points and it's a non-linear deal, okay? Technically what they had was something like this. Well, that was one, because that's down here. So it's going to be something like this. Because if you try and start this off level, then it's going to get weird. So it's going to drop, and then as long as you were somewhat close and just didn't draw it as a straight line, you were fine. Okay? That was the whole point of that question. Now, let's talk about F. pH of the soft drink is 3.37 after the addition of this, okay, which species has a higher concentration than the soft drink. So here's the deal. Go back to here. What was the pKa value? 4.77, right? So your pH is what, 3 point something?
Yeah.
So what has to happen to get a pH below this? Which of these numbers has to be bigger?
HA.
Your Ha has to be bigger. Why?
Because you need to be less than 1.
Then you're taking the log of a value less than 1 to drop that pH below the 4.77. Because if your anion concentration is bigger than your HA, what's going to happen? The pH would be above 4.77 because you would be taking the log of a value bigger than 1. Okay? Got it? Okay, so let's briefly talk about the multiple choice questions. So, you've got 8, 9, 10, 11, and 12. So, give those a try. The beauty of it is this requires no calculations.
You want to turn off the camera?
Okay, so what do you have on number 8? A, B, C, or D? Fuzzy. Huh?
Yes.
What?
Yes. Only to see him. I put A, but I don't know. I was just kind of circling.
Okay, so let's look at this graph. So, here's the normal one, right? Now, look at what this is. Number of molecules, and this is speed, right? So, what are you going to do to the sample? Are you going to remove the number? Are you going to change the number of molecules? No, so I'm still going to have the same number of molecules, right? Okay? Now, the whole key to this is that you're going to lower the temperature. Okay? So as you lower the temperature, what's going to happen to the average speed of the particles?
Slow down.
It's going to become less. So if you choose A, if you choose this one, that means you're making more of the particles have a higher speed. Because it's going to be the same area, but you get a wider distribution. So if you lower the temperature, the average speed is going to do what? Decrease. So what's the right answer?
D.
D?
Yes.
D as in done.
Yes.
Yes. So
I got
D
that
is the
right.
correct answer. Okay. Because that's the only one that shows, number one, it should be about the same area because it's the same number of particles. So B has some merit, but what's wrong with B?
Less molecules.
Yeah, you have less molecules. Okay? B would be a situation like if you had a balloon and you poked a hole in it, but you kept the balloon at the same temperature. B would be the correct answer there. Okay, so let's talk about number 9, little thermochemistry. What do you have for number 9? Wheels.
B.
B is a beautiful answer. Okay? Temperature of the metal drops more because it has a lower specific heat. Thermal energy stays the same. Now, number 10. Now, here's what's tricky about number 10. Okay? The whole key to about number 10 is one statement. And it says that all of the following statements are true. Okay? All of these are true. You're not picking the one that's best, okay? Or picking the one that's right, or picking the one that's wrong. So this is a subtle twist that they'll do on these questions. All of these statements are true. So we're not picking the one that's wrong. We're not picking the one that's, well, no. So first off, mass spectrometers work by, imagine this. Imagine that I've got a bowling ball, okay, rolling along, and I've got a blow dryer here. And I'm going to hit the bowling ball with the blow dryer. Okay, it's going to deflect a little bit. Imagine that I'm rolling a ping pong ball across here. And I put that in front of the blow dryer. What's going to happen? Boop! It's going to be over there. So, how mass spectrometers work is that you set up a field, okay? A charged field. So only the charged particles interact with this. So basically, what you're looking at is that the more they're deflected, the smaller the mass. The less they're deflected, the bigger the mass. So that's why it's called a mass spectrometer. So, viewing that, what's the correct answer on number 10? Nicola?
I want to see.
You should go with C. Okay? Now, I has a higher first ionization energy than TE does. Does that make any difference in this graph? That's a true statement. It is. Okay? But it's not relevant. Okay? So the only one that really makes any sense there is C, because of the fact that, and you can look at the periodic table and figure out the atomic number and mass number and all that good stuff. But that's why you have that gap on 127 and 129, because there's nothing there. Okay, number 11, what do you have? Katie? B, beautiful answer. Okay, spot on. Conjugate acid-base pair, that's B. Why isn't it A?
That has it's a difference of 2 hydrogen.
Yeah, it's a difference of 2. Okay. We seem to be on a roll here. So this is stuff that we just talked about. Sam Emerson, your answer to number 12.
B.
Beautiful. Why?
Because the signs are the same, so it's temperature dependent, and they're both positive, so it's
Depending on
high.
There you go. Okay. Wow. Hour and a half. We're good. Go home. Sleep in the morning.
Goodbye, everybody.